Happy welcome to everyone. In this session, I would like to discuss about Minimax algorithm, which is commonly used in artificial intelligence. I myself are Dhanalakshmi, Assistant Professor, Department of Artificial Intelligence, MITS College. In this lecture, we are going to discuss about what is in search, what is adversarial search, how it is differ from normal search, what are the algorithms used under under adversarial search, then Minimax algorithm, followed by terminologies used in Minimax algorithm, implementation of an algorithm, how to solve a simple example, at last properties and advantages, disadvantages of Minimax algorithm. So as we all know about searching, searching is the process of navigating from start state to goal state by traversing sequence of actions. Ultimately, it reaches the goal. A search algorithm takes a problem as input and returns a solution in the form of action sequence. Once the solution has been executed, the agent will formulate a new goal. A solution to a problem is an action sequence that leads from the initial state to goal state. Quality of the searching is measured by the path cost function, and optimal solution has the lowest path cost among all solutions. Now we come into adversarial search. How it is differ from normal search? In a normal search problem, that is in a single agent environment, the optimal solution, as we know already, it starts from start state to goal state. The optimal solution would be arrived the sequence of actions leading to a goal state. That is obviously terminal state said to be a win state. In an adversarial search, it is commonly used in all artificial intelligence, machine learning, even deep learning, computer visions. So why it is used? It is used to make optimal solution in multi-agent environment where agents have conflicting objectives. In the case of competitive environment, each agent needs to consider the actions of other agent or an opponent and how it affects the outcome or how it affects one's profit. Where can be used? Probably this kind of search commonly used in games where the goal is to find the best move for a player, assuming that opponent also plays optimally. Even in the worst condition also, it takes the optimal solution. So adversarial search probably in a competitive environment where each agent has conflict in goals. That rises to an adversarial search. It is used in game theory. As I said, games are the good examples of adversarial search since AI games each states are easy to represent, whereas in the physical games are somehow complex states to describe. Then agents are restricted to small number of actions. Outcomes are defined by precise rules. In the case of physical games, states are much more complicated descriptions and large range of actions, rather imprecise rules to be defined. Let us consider the games given below. 8 puzzle game, tic-tac-toe and chess. Out of these three games, which are comes under adversarial search? Can you have a guess? In the case of 8 puzzle game, when a player plays, no one disturbs the move or no one interrupts. But in the case of tic-tac-toe, chess, board games, player 1 plays X followed by another player plays his sign O. So these two happens alternatively. The move disturbed by another player. As like the same chess game, player 1 moves one coin, alternatively player 2 plays another move. So these two games are comes under adversarial search, but 8 puzzle game is not. In the case of simple game tic-tac-toe, finding the solution, which means that either of the player plays any of his sign in a row said to be a win state. So searching happens in a competitive environment. Placing their signs in a row is said to be a win state. So in the case of tic-tac-toe, chess are to be considered as adversarial search, but 8 puzzle game is not. So these two works under competitive environment where agent goals or conflict with each other. One among the examples of an adversarial search is Minimax algorithm. So we knew how to find a solution, how to derive a solution for an adversarial search. Optimal solution can be obtained by either heuristic or else pruning method. So Minimax algorithm uses heuristic method to find the optimal solution. Minimax algorithm is a recursive or backtracking algorithm which is mainly used in game theory and decision making. It's a two-player game like a chess and tic-tac-toe or board games or strategic games. The main objective of this algorithm is to find the best optimal move even in the worst case scenarios, that is whether both of them place optimally, even if they both place optimally. It's a two-player game. In the case of Minimax algorithm, the players are called it as max and min. Max player aims to maximize his profit. At the same time, min player whose goal is to minimize his loss. So it's a two-player game. Each player takes turn alternatively. This is works under different environment, especially in a deterministic, zero-sum games of perfect information, and fully observable environment, which it means deterministic environment, which easily can determine the future state from the current state. So there are other deterministic, that environment may be of deterministic or stochastic, which means that each move, future move can be predictable from the current move. That is deterministic. But in the case of stochastic, moves may be dynamic. Even the agent cannot be identifiable or cannot be predictable. It is out of action. Then zero-sum games of perfect information. In the case of Minimax algorithm, if a player wins, one player wins, obviously the other player loses. Net profit of the game, net payoff of the game is zero. That's why it's zero-sum games with full information. Every information is known at all the state and fully observable environment. So each state agent can be allowed to access all states at all time. So that is fully observable environment. So Minimax algorithms, for instance, we consider it can be worked under deterministic, zero-sum games of perfect information, and fully observable environment. As we know that it's a two-player game whose names are Max and Min. Max always aims to maximize his profit, and Min, whose goal is to minimize his loss. Each player aims to minimize the maximum possible loss. So, optimal solution can be obtained by minimizing the maximum possible loss, assuming optimal play by the opponent. Example, so this can be applied on tic-tac-toe, chess. So these are the board games. There are some strategy, there are some precise rules in the games, or the best examples for Minimax algorithm. Before getting into that algorithm, we should know some terminologies which are used under Minimax. As we know that game is the best example for explaining adversarial search in a competitive environment, that can be defined or that can be explained with a game tree. So game is defined as a kind of search problem with the following elements. S naught, the initial state. The initial state where the player can start their move. Player, yes, player takes S as a state and returns whether it's a turn for min player or max player, as in the case of Minimax algorithm. So Minimax algorithm, it's a two-player game where max finds the state for max or min. Actions, yes, it takes the current state as input and returns possible moves in a state. Result takes current state as well as action as an input. It's a transition function, returns a result of a move. Terminal is a function which takes S as a state and it finds whether the game is over or not by returning true or false. If it returns true, it means that the game is almost over, or else it returns false. The last one, utility function. Utility takes current state as well as player as an input and returns the final numerical value for a game that ends in terminal states for a player P. It returns either 0, 1 or -1. So possibly outcome of this function is win, loss or draw. As we know that Minimax algorithm, one player maximize his profit. Obviously the another one minimize his loss. So it can be represented as win +1, loss -1 and draw as 0. For constructing this algorithm, we need to have a game tree. For implementing this algorithm, we need to have a game tree. For game tree, we use initial state, action function, and result function. So we incorporate all these three functions together to construct a Minimax game tree. To implement this algorithm, as I said that game tree should be constructed. So it has to start with max node. Conventionally, we consider max player plays first in the board configuration. So we expand or traverse node from root node to the leaf node. Apply the evaluation function at each of the leaf nodes. So always leaf node has the utility values. Once it reaches the terminal state or leaf node, then the values are to be backed up towards parents node through non-leaf nodes. Based on the type of player, it takes either min value or max value. At last, that value propagated to the root node. This is the way you can find the value of minimax. As we knew that game tree should be constructed for implementing Minimax algorithm. As in the case of tic-tac-toe, it is too difficult to draw entire scenario. We take a simple subset of tic-tac-toe game tree. In this case, max player takes, conventionally we consider max player plays first, followed by then min player. We knew that it takes initial state, then actions to be needed to construct a game tree. S naught is the initial state. As far as game tic-tac-toe concerned, there are 3 by 3 matrix, 9 empty cells. Max player can place his sign in any one of the 9 empty cells. So there are 9 possible actions are there for max player. Then that is the initial state S naught. For constructing that game tree, so tree, we knew that tree consisting of nodes and edges. Here nodes represents the game state and edge represents a possible move. As far as this tree concerned, max player has 9 possible moves. Then he may place his sign in any one of the 9 empty cells. Then min player places O, alternatively takes followed by max min player. Place takes alternatively max placing his in X and min placing an O corresponding until it reaches the leaf node corresponding to the terminal state, such that one player can see his sign in a row, or else all blocks gets filled or all squares gets filled. That is said to be a terminal state. A value which is associated with that leaf node is called utility value. Higher value is good for max player and bad for min player. These are all with respect to max player. All utility functions are employed at the leaf nodes. So this is the way we can construct a game tree. In the initial state, there are 9 possible moves. So yes, not, there are 9 possible empty, there are 9 possible actions. As in the next state S1, min player has 8 possible moves. Likewise, recursively it goes on until it reaches the terminal state. For S0, it has 9 nodes. Then in the S1, 9 for min player has 8 states. So 9 into 8 number of nodes. Then S2, 9 into 8 into 7 number of nodes are possible in these cases. So successively it goes on. So number of nodes in the case of this game tree is 9 factorial. How could you achieve that optimal strategy? So optimal strategy can be determined from the minimax value of each node. How can you find the minimax value? It is the utility of being in the corresponding state, assuming that both players place optimally. From there to end of the state, end of the game, we call it as terminal. From there to root node. Obviously, minimax value of a terminal state is just its utility. Max value, max player always maximize his welfare and min player aims to get minimum loss. Min-max algorithm or minimax value of that particular node can be found by passing the current state into that, and can be found by applying the formula. If the current state is terminal state, if the current state is terminal state, then it returns the utility value of that corresponding leaf node. Or else, if the state is being played by max player, then maximum of all its actions, maximum of all its action after applying minimax algorithm to its resulting nodes. If it is in the min player, then minimum of all possible actions after applying minimax algorithm to its successors. So likewise, we can find the minimax value of each non-leaf nodes. This is the pseudocode which is used to find the minimax value of a given node or minimax value of a node. So it starts with decision. It takes the state as input and returns the best move or optimal move among the all possible actions. Obviously, max player takes its turn first, so it returns the argument of max for all possible actions after applying min value to its successor or min value to its children. It's a recursive algorithm, and backtracking, it takes the turn to min value function and returns the utility value. If the state being transferred to the method is terminal state, then it returns the utility value. Or else, initially, minimax value of that particular node is assigned to infinitive. Then for each actions in that particular state can be found by finding the minimum value of the current value of that node, and maximum that value is compared with maximum of all its children. Likewise, if it is max function, then it finds as like the same way and returns the minimax value of that root node. This is the way algorithm is being implemented. Let us consider the reduced form of minimax algorithm. The same thing. Here there are two different types of triangles are being used. Upward triangle. Upward triangle are said to be max player, that is triangle facing upward direction, and triangle facing downward direction are said to be min player. Always max player takes his turn to play first. Max player takes the possible actions or A1, A2 and A3. There are three possible actions for max player. He can choose the best out of A1, A2, A3. For the best reply of A1, action A1 is for min player is B1, B2, B3. So B1, B2, B3 are the possible moves of min node B. Likewise, for C, C1, C2, C3, D, D1, D2, D3 and so on. In the last state or in the last level, some values are attached to the node that are said to be utility value. Now, how can we find the minimax value of all nodes? Or how the max can find its value? So that can be found by best move even in the worst payoff, which it means that both the player plays optimally. Min player always aims to both the goals are conflict with each other. Min player wants to minimize his loss. Max player wants to maximize his profit. So here leaf values. So once the node has to be traversed from root node 2 until it reaches the leaf node. And the values are being backed up towards its parent. Now here initially in the algorithm what we said, this value will be initialized to infinitive. Then this value is compared with the maximum of its node. Here the value is 3. 3 is compared with infinitive. So now the minimax value of B is 3. Again, this is for all possible actions of this particular branch. Then 3 is compared with 12. 3 is compared with 8. This is the turn for min player. So it takes the minimum value of all its children. So finally 3 is backed up for the value of B, min player. As like the same case here, among 2, 4, 6, among all these three values, the minimum value is 2 is being backed up or propagated to its parent C. Likewise, in the case of D, minimum value of its children is 2 being propagated to the node D. Since it's a turn for min player, it takes the minimum value. Now the turn for max player. Always max player wants to maximize his profit. So out of 3, 2, 2, among all these possible actions, it takes the best move as A1. Since the value of A1 is 3, so for this node it takes 3. So likewise, problem can be solved by using Minimax algorithm. It's a board game or strategic game. There are some specific rules. Every state can be easily monitored or determined by another agent. So that's why it is under deterministic and fully observable. This is zero-sum game. Here, one player wins. Obviously, no other way. Other player should lose. So this is the way min player in the first step, left branch node, it follows depth first search. Since Minimax algorithm explores depth first search, it starts from it starts from root node and travels all the way to the leaf node and then backed up or propagated to its children to re-explore all other nodes in the tree. Likewise, it completes its left subtree, then it goes on with others, likewise all other, then it ends up with root. So values are propagated to its parent until it reaches the root node. So likewise, value is being calculated for non-terminal or non-leaf nodes. Next, properties of Minimax algorithm. In the case of Minimax algorithm, here properties of Minimax algorithm. So Minimax algorithm is complete. When it completes, if the tree is finite or if solutions can be found, then it is said to be finite. Yes, Minimax algorithm is complete. Tree is finite since it is in a deterministic, so it's a finite solution can be found, then it is said to be complete. Optimal. Yes, it is optimal. Both the player plays optimally. Then time complexity of Minimax algorithm. Since it explores depth first search, it travels from root node and till to the leaf node, and all it explores all nodes in such a way. So the time complexity of Minimax algorithm is order of b power m. So order of b power m, where b is the branching factor and m is the maximum depth of the tree. So branching factor is nothing but number of possible moves for that particular level, number of possible actions for that particular level. So branching factors, if more branching factors, obviously it takes time. Space complexity, as we know that it follows depth first search, it follows the same of depth first search, so that the space complexity of depth first search is order of bm. Here also the same as order of b into m. We knew that b is the branching factor and m is the maximum depth of the tree. At last, we come to the end of the slide, end of the presentation, that advantages and limitations. What are the advantages? So Minimax algorithm can be applied onto board games. Simple board games, it's a strategy game. So guarantees for optimal play for both the players. Limitations. Computationally expensive for large game tree. So as we knew that this can be applied for tic-tac-toe as well as chess games. In the case of tic-tac-toe, we have very limited states. 3 by 3 matrix, possibly 9 empty squares, which means that there are 9 factorial nodes are there. Branching factors also less since 9 possible moves, and then depth of the tree also limited. But practically it's limited for small branching factor and manageable depth. But as in the case of chess game, for instance, consider there are 35 possible moves, there are 35 nodes, and limited to each player limited to branching factor is up to 35, and each player limited to 50 moves. Each player means both the players can have up to 100 moves. Then number of nodes are 30 power 100. So as branching factor increases and depth increases, obviously efficiency of that algorithm also degrades. As we said already, that optimal solution can be obtained either by heuristic or by pruning method. So the next, these limitations can be overcome or improved by using alpha beta pruning. So unnecessarily, instead of traversing all nodes, we can just remove or prune the nodes which are not essential or not giving impact onto the outcome. So that will be explained or that will be discussed in the forthcoming videos. So these are the content which are taken from Artificial Intelligence, a Modern Approach, 3rd edition by Stuart Russell and Peter Novick. Thank you.